Also, are we on the motivic Galois group of a number of fields? So first, I would like to begin talking about Lamdan's conjectures regarding motivic Galois groups. There is a hypothetical locally compact topological group Lk, the Langlands group of a number field K, whose equivalence classes of the n-dimensional complex semi-simple representations parameterize the equivalence classes of automorphic representations of GLN AK, the general linear group on the ring of Adels AK of K. It is expected, due to Langlands, Deligne, and Clausel, that there are relations between the motivic Galois group of K and certain automorphic representations of general linear group on AK.
Sorry, Semih.
Yes.
Could you make it full screen?
Sure. This one, right?
I think just be, yeah, I think this is good too. But
is there a way to do it through Zoom?
no, I think it's just
okay.
your browser. This is great too, but if there was a full screen.
See this.
I see something close to that, the minus plus and then something and then some. Yeah, no, to the right of it. No. What is the one to?
This one. Yeah, this one is this.
Oh.
That's all it does. It's.
Yeah.
I still can't.
This is great too. Just yeah, this is great as well.
Okay. Okay, the following conjecture due to Langlands appears in James Arthur's article, Principle of Punctoriality. There is a continuous homomorphism from the Langlands group Lk of a number field into the motivic Galois group of K, which is defined over the absolute Galois group of K. And the same assertion holds for all local completions of the number field K at all finite and infinite places nu of K. It is also conjectured that automorphic representations form a Tannakian category, and since every F-linear Tannakian category T is the category of representations of some group GT associated with T, Langlands group Lk should be the group whose representations yield automorphic representations. Therefore, the above-mentioned conjecture of Langlands states the expectation that automorphic representations and theory of motives are related and states a candidate for this relation. The aim of the talk is to briefly introduce the motivic Galois group and state a potential answer to Langlands' conjecture regarding the relation of Langlands group and motivic Galois group. So first, I'll start with some background, talking about the main ingredients. That's Tannakian categories, motives, motivic Galois group, and Grothendieck standard conjectures, and other background material. First, motives. The category of motives is motivated by a quest to generalize Galois group to geometric objects in algebraic geometry, namely varieties. Just as Galois group of a number field acts on points of a field, motivic Galois group is to act on varieties. The category of motives to be constructed takes as objects varieties. The notion of morphism among varieties is replaced with correspondences, which are generalizations of morphisms. Now, graph of a map is something that lies in the product of varieties, and correspondence is also going to be some specific subset of the product of varieties. In addition, though, we would like to include properties investigated by intersection theory. And because of that, it is more natural to work with correspondences, which are algebraic cycles in the product of the two varieties. And because one is interested in these intersection theoretic properties, relation between intersection theory and cohomology, one takes varieties as objects modulo some equivalence relations, such as numerical equivalence. In order to understand what the underlying ideas behind these are, one needs to go over Grothendieck's standard conjectures. Okay, so first, a sort of rough example of a variety over R, the real field, is the unit sphere defined as the zero locus of the polynomial x squared plus y squared plus z squared minus 1. But note that this is not a projective variety, but it is the affine part of the projective variety, x squared plus y squared plus z squared minus w squared equals 0. Note that it is not the graph of a function, but it is a correspondence between r and r squared. Strictly speaking, it is going to be called the correspondence of grading 0 from r to r squared, and the sphere is a cycle of codimension 1 in R3. On the other hand, z equals square root of x squared plus y squared is a function from r squared to r, whose graph is the cone, which is part of the variety and correspondence given as zero locus of x squared plus y squared minus c squared. And the intersection locus of these two varieties can be seen in this graph. It consists of two circles in this case. X squared plus y squared equals a half equals z squared. Okay, so now let's go over standard conjectures. First, weak form of conjecture 1, which is going to be named Cx. The Kunev components of the diagonal are algebraic. This means for a variety x of dimension n, let delta be the diagonal in x times x. Kunev decomposition implies that the nth cohomology of x times x can be written as the direct sum from index I running from 0 to n of ith cohomology of x tensor with n minus ith cohomology of x. Now, using this decomposition, the diagonal delta can be written as a sum of pi I, where pi I are the Kunev components of delta. Weak form of conjecture asserts that these components come from algebraic cycles. By algebraic cycle is meant an element of the free abelian group generated by subvarieties of the variety x. And a technical note to add here is that what is meant by a subvariety is a closed integral subscheme. Now, standard conjecture 1 of Lefschetz side, which is going to be called AX. Let X be a smooth and projective variety, and C in the second cohomology be the class of a hyperplane section. By cup product in cohomology, this section defines a homomorphism by taking n minus ith fold cup with C, defining a map from the ith cohomology to the 2n minus ith cohomology for I less than or equal to n. It has been proved by Lefschetz that over complex field, this is an isomorphism. First part of the conjecture is that this is
n is the dimension of x?
N is the yes. Yeah. First part of the conjecture is that this is an isomorphism for all characteristics. The second part of the conjecture is that this is an isomorphism for all characteristics. The second part is that for I equals 2j, this map induces an isomorphism, or equivalently, an epimorphism on cohomology classes of algebraic cycles. Now, conjecture Bx is equivalent to conjecture Ax. What is called the lambda operation of Hodge theory is algebraic, and there is an algebraic cohomology class lambda in the cohomology of x times x, such that the map lambda from the cohomology of x to cohomology of x, which is obtained by lifting a class from x to x times x by the first projection, coupling with lambda and taking image in the cohomology of hx by the Gysin homomorphism associated to the second projection. Now, the relation between conjectures Bx and Ax. Bx implies Ax. Algebraicity of lambda implies that of lambda to the n minus ith power, which provides an inverse to taking a cup product with c n minus I times. Then it is shown that conjecture A holding for x times x implies conjecture B holding for x. And this proves equivalence of conjectures A and B. And just here note that Ax implies conjecture A on x times x. This can be concluded by considering QNF decomposition in cohomology. Furthermore, conjecture Bx is stable for products, hyperplane sections, and specialization. And last, conjecture Bx implies Cx. Then there is the Hodge type conjectures. This conjecture asserts that a symmetric bilinear form restricted to algebraic cohomology classes in 2J cohomology of X that lie in the kernel of taking cup product with C n minus 2J plus 1 times, formed by taking the pair XY to this intersection product or cup product in the top cohomology defined up to sign. This bilinear form is positive definite. Here, C is a hyperplane section of X, hence an element of the second cohomology, and K is the isomorphism between top cohomology and the coefficient field QL. Now, I'll go over motivation for adequate equivalence relation. In constructing theory of motives, one would like to consider varieties as basic building blocks of objects of a category, as discussed earlier. As morphisms, one is using correspondences, which are cycles in the product of two varieties of appropriate codimension. Transpose of graph of a morphism F from a variety Y to a variety X has codimension of X in X times Y. And one has to invert direction for in correspondences, one is working with a contravariant functor by choice. One would like to see these morphisms, which are cycles, as equivalent to fit the intersection theoretic framework. Therefore, one considers what is called adequate equivalence relation on the morphisms. Now, an adequate equivalence relation is described below. Elements of the free abelian group generated by codimension I subvarieties of a variety X are referred as cycles of codimension I, and cycle refers to cycles of all possible codimensions. An equivalence relation on cycles of codimension I in a variety X for each I is called an adequate equivalence relation if it is compatible with grading and addition. This means if a cycle is defined as a sum of cycles Ci, where each Ci is a cycle of codimension I, such a thing is equivalent to a zero cycle if and only if each of the summands is zero, equivalent to zero. But then there is compatibility with products, and this is defined by the following statement. If a cycle Z is equivalent to 0 on X, then Z times Y is equivalent to 0 in cycles on X times Y. And then there is compatibility with projections. If a cycle Z is equivalent to 0 on X times Y, then when we push that cycle to project it via inverse using projection map, then what we obtain is still equivalent to 0. Then there is the moving lemma, which says that if Z and W1 through WL are cycles on X, then there exists a cycle Z prime, which is equivalent to Z, such that Z prime product of Z prime and WI is defined for all of the cycles for index I through L.
And can I ask a question? Sorry.
Yes.
I'm confused about the first condition. So you're saying that a sum is equivalent to 0 if each component, if its summand is equivalent to 0.
Yes.
So is this sum, I mean, if I write,
it's the sum over the codimensions. So because we're taking a free abelian product generated by cycles of any dimension.
Okay. So you group all of the same dimensions.
Right.
Okay.
So this sum will be equivalent to 0 if each of the summands of a specified codimension constitute a cycle of equivalent to 0.
Okay, so your abelian group is generated by all cycles, not a fixed codimension.
No. It's by code, it's graded by codimension.
I see. Okay. Thank you.
Mm-hmm. Now, the consequences of adequate equivalence relation. If an equivalence relation on cycles is adequate, then one can form quotient groups on cycles modulo cycles equivalent to 0, obtain a ring with product induced from intersection of cycles. Now, a morphism F from X to Y of smooth projective varieties over K induce homomorphisms F lower star and F upper star, where F upper star is a homomorphism of graded rings. A correspondence Z from X to Y of degree R induces a homomorphism from the equivalence classes of cycles of codimension I in X to equivalence classes of cycles of codimension I plus R of Y, and equivalent correspondences induce the same manner. Now we have examples of adequate equivalence relations. These are rational, algebraic, homological, and numerical equivalence. An adequate equivalence relation is said to be finer than another if a cycle equivalent to 0 under the first relation is also equivalent to 0 under the second relation. And the stated adequate equivalence relations are related in this fashion. So here, numerical equivalence is the finest and rational equivalence is the coarsest. This is what is known. When the field is an extension of Q, there is another adequate equivalence relation called smash nilpotence due to Voivodsky that lies between algebraic and homological equivalence. And Cho groups are cycles modulo rational equivalence. And note that rational equivalence can be seen as equivalent to equivalence by divisors of rational functions. Okay, so now I'll go over the motivation for considering Weyl cohomology. Both due to Weyl conjectures and because intersection theoretic and combinatorial properties arise in cohomology theories, one would like to consider cohomology theory in relation to varieties. There are various cohomology theories, but they share certain properties that is described in the notion of Weyl cohomology. Furthermore, the cohomology functor is essential for constructing motivic Galois group. A Weyl cohomology theory is a contravariant functor H from the category of smooth projective varieties over K into the graded vector spaces over a field F that satisfies the following. The ith cohomology of X is of finite dimension and is 0 for all I outside the range 0 and twice the dimension of X. Then there exists a product called the cup product, which takes a pair of elements in cohomology to another element in cohomology that is graded, in the sense that if A is in the ith cohomology and B is in the jth cohomology, then the A cup B is in the I plus jth cohomology, and it is super commutative in the sense that if we cup B with A, that's the same as -1 to the I times jth power times, that's a type of A cup B. Then the other property is Poincare duality, which says that there is a trace isomorphism from the 2D cohomology of X to the field, such that the pairing taking the ith cohomology of the 2D minus ith cohomology together with the cup product to the 2D cohomology, and then applying the trace map, this composition is a perfect pairing, meaning that the map sending ith cohomology to the homomorphisms from the 2D minus ith cohomology to the field defined above is an isomorphism. Then there is a Kunev formula, which takes the cohomology on X tensored with cohomology on Y to the cohomology on X times Y, using the should we call this the pullback of projection maps tensored together. This map is a graded isomorphism. Then there are cycle class maps from Chow groups of cycles under rational equivalence to cohomology classes, taking the ith Chow group to the 2 ith cohomology, which are functorial, in the sense that for a morphism of in the category of smooth projective schemes or varieties over K, F from X to Y, then F upper star composed with this class cycle map, gamma Y, is the same as gamma X composed with F upper star. And similarly, a similar rule also holds for F lower star. Then there is multiplicativity, which says that this cycle class map on X times Y, acting on a subvariety Z times W, is the same as the tensor product of the class cycle map of X acting on Z and Y on W. And also this is compatible with intersection product. So the class cycle map maps the intersection of A and B to the cup product of the images of A and B under the class cycle. Then there is also compatibility with points, in the sense that the trace of the class cycle map on P is the same as I composition, the degree map, or in other words, we have this commutative diagram. Then there is finally weak Lefschetz and hard Lefschetz. Weak Lefschetz says if I is a smooth project, I of Y included in X is a smooth hyperplane section, then I upper star, which takes the ith cohomology of X to the ith cohomology of Y, is an isomorphism for I less than D minus 1 and is injective for I equal to D minus 1. where G is the dimension of X. And a hard Lefschetz says the Lefschetz operator L of alpha, which is defined by cutting the image of Y under the class cycle map of X, coupled with alpha, induces isomorphisms by operating L d minus I times for I between 0 and d inclusive. So this defines what a wave cohomology theory is. And we have examples of classical wave cohomology theories. There's Betti cohomology, which is the singular cohomology group, where we take the complex manifold underlying X, or the analytic manifold underlying X. Then there's classical de Rham cohomology. There is algebraic de Rham cohomology. There is étale cohomology. And for K perfect fields, there is crystalline cohomology, where capital K is the field of fractions of the bit ring of WK. And also, this detail, maybe I'll still mention it, the variety, K, the algebraic closure K points of the variety X means X tensored with K bar, and X K bar QL. Here, the prime L is different than the characteristic of the field K. Now we come to finally the definition of motivic Galois group. Motivic Galois group of a number field is described as the tensor equivalences of the fiber functor of the cohomology functor. Motivic Galois group turns out to be a semi-simple Tannakian category, and the definition of Tannakian category is discussed next. And of course, this choice, we went over the various adequate equivalence relations, because they define correspondences differently, classes of correspondences differently, will yield different motivic Galois groups. And there are conditions that we will go over later that ensure when this category turns out to be semi-simple Tannakian. Okay, Tannakian categories. First, we'll start with the basic conditions. First, the category has to be a tensor category, and by a tensor category is meant a category equipped with a functor from the category of C times C through the category C. And this functor needs to satisfy certain properties. Specifically, it needs to have compatible ACU constraints. This means there's an associativity constraint with it, which is a morphism from here to here for all triples X, Y, Z of objects in the category C. Then there is a commutativity constraint, and then a unit object such that taking product with the unit object is fully faithful, and there are isomorphisms Lx and Rx mapping which are from X to 1 tensor X, or from X to X tensor 1. And these are called unit constraints, such that these isomorphisms on the unit object coincide. And these need to satisfy appropriate commutative diagrams called compatibility constraints. And the reason for making these requirements is so that we can define these products irrespective of placement of parentheses and position of objects in the product. Just to give the detail, associativity constraint is expressed in this in the commutative diagram below. It's called the pentagon axiom. And again, this commutativity of this diagram assures that we can shift parentheses in a fourfold Yeah, a triple product with 4 items, and such that the shifting of parentheses will not matter under the chosen associative constraint. Then there is, to give an example, there are other commutative diagrams, but the most important one is this pentagon and then this hexagon, which is a competitivity of associativity and commutativity. Now, if the contravariant functor mapping T to morphisms from T tensor X to Y is representable, then underlined Hom XY denotes the representing object, and then this is called internal Hom functor. And one sets the notation X V as the underlined Hom XY. Now, an ACU tensor category is rigid if it possesses internal Hom objects, and the canonical morphisms switching tensor functor with the internal Hom functor in this fashion are isomorphisms, and all objects are reflexive, and this means that the canonical map mapping X to XBD is an isomorphism. Now, a neutral Tanaka category over K is a rigid abelian K-linear ACU tensor category C for which there exists an exact faithful K-linear ACU tensor functor omega from C to K to the category of K vector spaces, finite dimensional, and any such functor omega is said to be a fiber functor. Any neutral Tanakian category is equivalent in possibly many different ways to the category of finite dimensional representations of an affine group scheme. And precisely this is the following theorem. The functor out tensor omega of K algebras is represented by an affine group scheme, and the functor mapping C to red KG defined by omega is an equivalence of tensor categories. Now, the full definition of Tanakian category involves gerbs, a concept developed in relation to non-abelian Galois homology, but I won't go into those technical details. Now, semi-simple category, in order to define semi-simple category, first we need to define what a simple object is in an abelian category. An object is simple if it has no proper non-zero sub-objects. It is semi-simple if it is a direct sum of simple objects. Now, the result on motivic Galois group, the first result, is due to Dilin, Min, and Saavedra, and it is that the category of motives, MK, after an adjustment of signs in commutative constraint, is a semi-simple Tanakian category open Q. Now, Jansen's result on motivic Galois group is the following. The category of motives over K is an F-linear pseudo-abelian category. And the main result, again due to Jansen, is that the category of motives is a semi-simple abelian, the equivalence of the following. The category of motives over K being the semi-simple abelian category is equivalent to the second condition and the third better known condition, the relation that motive correspondences should be seen under as equivalent is numerical equivalence. This other condition says that cycles of the dimension x on x times x is a finite dimensional semi-simple F algebra for every continuous. Now, the result of motivic Galois group, this is the conclusion. Assuming the standard conjectures, in particular QF components of the diagonal being algebraic conjecture, which is conjecture CX, Jansen states that the category of motives with respect to numerical equivalence is a semi-simple F-linear Tanakian category. cohomology functor with coefficients in some field L from the category of motives of smooth projected varieties over K with correspondences modulo numerical equivalence being the morphisms serves as a fiber functor, and Tanakian duality formalism gives a group scheme over L as the group of tensor automorphisms of this cohomology functor. This is the absolute motivic Galois group of K. But also note that any motive M generates a Tanakian subcategory of the category of motives, and Tanakian formalism gives a group scheme, the group of tensor automorphisms of the cohomology functor restricted to this Tanakian subcategory. This is the motivic Galois group of a specific motive M. Now, I'm going to state the main result. There's a map from Weil-Arthur-Idel group into the Taniyama group, which is isomorphic to the motivic Galois group of CM motifs, given as the following composition, where here WAF is the Weil-Arthur-Idel group, and IF is the non-abelian Idel class group described in Kedel's papers, and WF is the Weil group, and TF is the Taniyama. The map fits into a commutative diagram with the group GF being the map constructed from fiber products. So this is the resulting. And here, LF is the Langlands group, KF, DF, and GF are just these groups described in Arthur's construction of Langlands group. And this upper commutative diagram is described in Kedel's paper, and the map from Weil group to Taniyama group was known before. Note that the significance of the result in relation to Langlands conjecture is the following. Conjectural Langlands group is captured between Weil-Arthur-Idel group, whose construction is known and concrete, and a group that is conjectured by Arthur to be the motivic Galois group or a group closely related to it. We will be discussing the parts that go into constructing this commutative diagram. And within my thesis, many of the foundational topics that go into defining these groups in this diagram are discussed. So the first commutative diagram is this one. Here, the construction of Weil-Arthur-Idel group is dependent on a Lubin-Tate splitting, but all this extra information is suppressed in this notation for simplicity. And here, WAK is the Weil-Arthur-Idel group, LK is Langlands group, WK is Weil group, and IK is the non-abelian Idel group constructed by restricted free product in a fashion that is similar to the construction of the abelian, the better known Idel group. Weil-Arthur group, WAK, and Idel class group IK is defined via a restricted free product coming from groups in non-abelian class field theory with components of WAK containing SU2 term in addition to the components of IK. The map from WAK to IK omits to SU2 component, and the map from IK to WK is a non-abelian analog in the sense of form of non-residual symbol of class field theory. Ikeda in his paper deduces that Langlands group defined by a set of conditions should fit inside the commutative diagram. I will simply assume that this commutative diagram exists. Assuming only non-abelian class field theory, the map given by the composition of the map from WAK to IK and from IK to the Weil group exists. Now, the lower portion of the commutative diagram in James Arthur's construction of Langland's group, there are two exact sequences mentioned here. These exact sequences are obtained from a fiber product taking over an indexing set CF, where for each element C of the indexing set, one forms an extension of the Weil group and Taniyama group by appropriate groups that these groups act upon. And now the construction of the second exact sequence is related to the map from the Weil group to the Taniyama group. The construction of this map is also homological in nature. In Arthur's article, The Principle of Factoriality, it is stated that the construction of GF and LF parallel each other. Hence, there is a homomorphism from LF to GF. It is expected that GF is either the motivic Galois group or a group closely related to it. Furthermore, if the homomorphism from LF to GF does fit into a commutative diagram, since KF sits injectively inside LF and DF sits injectively inside GF, if the homomorphism fits the map from the Weil group to the Taniyama group, as mentioned, then this diagram is known. Now, the connection to the motivic Galois group. First of all, the Taniyama group itself was shown by Gilin to be isomorphic to the motivic Galois group of CN motives. It is expected that the group GF in the exact sequence above is related to the motivic Galois group of the number field, may be isomorphic to it, as guessed by Arthur in his article Principle of Factoriality. Okay, that's the end of my talk.
Thank you very much, Semih, for your very nice talk. Dear audience can unmute your microphone so that we can all thank Semih.
Thank you.
Okay, if you have any questions, you can ask now.
Can I just see the references, please?
Yes, sure. There's Andre Eves, some articles about Andre Eves. There's James Arthur, Note on Automorphic Langlands group and Principle of Factoriality. Then there is Delin connecting categories, more Delin. And for motifs, there's Michel de Mouzour's article, and there's Ikeda's papers.
Yes, I want to see this. And then yours, right? So is it your thesis or?
This was my thesis, yes.
So is it written up or, I mean, is it?
We're preparing the article with Professor Ikeda.
Okay. So will you share your slides with us?
Yes, sure.
Great, thank you.
I will email them to Ali.
Sure. Do you want me to just send it to Hadi or everyone?
So what do we do? Do we usually post on the
Oh yeah, right.
on the site?
Yeah, I see.
If it's okay for Semih, I don't know.
Yes.
Yeah, I forgot that we upload them. So, yeah. And if there are any more questions, please ask. If not, then thank you again, Semih, for your fantastic talk.
Okay.
And so with that, I say goodbye to everyone. Thanks.
Goodbye, thank you.
So like I said, there is going to be almost the Persian holiday will start soon, and there is going to be a long gap again in the sessions. So I think we'll return a little after mid-April, and I'll
Have
make
a
an
nice
announcement.
holiday.
Yeah, thanks.
Have a nice-
And happy spring to you as well, and happy New Year to all the Iranians. Great, thanks.
Thank you. Bye.